Welcome and thank you for joining our project overview for our physical two-factor authentication system. This project was pursued as a part of the Integrated Systems Design 2 course in spring 2024. The team comprises of Sahil Manga, Bolu Tijani, Philip Bernola, Cameron Morrison, and Blake Walker.
In today's world, where security is more critical than ever, we've enhanced the traditional RFID security system by incorporating facial recognition technology. This dual-layer security approach addresses the prevalent issue of RFID tag duplication and theft. By requiring both a tag scan and a facial match before granting access, our system ensures a robust defense against unauthorized entries, providing peace of mind and an added layer of security. This system aims to tie classic RFID scanners with modern computer vision technology to provide access to homes or other types of private property.
There were a few goals that guided the construction of this system. The main priority was ensuring a high success rate for all functions that were designed into the system. This means that we aimed for a high success rate of granting and denying access, as well as ensuring the robustness of our deadbolt system as well. Another goal was to encompass our system in a practical housing that is consumer-friendly, further reinforcing the idea of this being a marketable technology. Now that we've discussed some of the basic guiding principles of this project, let's break down the operation of the system by watching a recording of the live demonstration.
Before a system can be used in its normal operating mode, the user first needs to be set up. The system administrator can access the HDMI port and by using a keyboard and mouse, start the initializing program through the command terminal. The user begins by first scanning their RFID card and then typing in their first and last name. After this, the keycard is swiped once more to write the information onto the card. Lastly, the user is prompted to take 5 pictures, with each picture being at a slightly different angle.
Under normal operation, the user will scan their RFID credentials and keep their face in front of the camera. After the user scans, the system cross-references the live feed with their pictures from when their credentials were initialized to verify identity. In the event of a successful verification, the deadbolt will open and remain open for at least 10 seconds. In the event that the door is not closed after 10 seconds, the deadbolt will remain unlocked until the magnetic door sensors are aligned, indicating that the door is closed.
Access is denied if the user does not match the user's picture stored in the database. Under this scenario, the deadbolt lock does not open and a red LED flashes at the user.
And now let's walk through a scenario where the system encounters invalid credentials. Imagine someone attempts to access an area with an unauthorized RFID tag. Our system detects this anomaly and denies access, effectively stopping potential security breaches.
The diagram of our system is fairly straightforward. We begin with a Raspberry Pi 4, which is the heart of our system. The Pi is powered using a Geekworm X1202 uninterruptible power supply, which is powered using a standard USB-C connection. The Pi has standard peripheral connections, including a monitor and wireless mouse and keyboard. Also connected to the Pi is a standard Pi camera, which is connected via a ribbon cable to the Pi's camera module port. There are 3 devices connected to the Pi's GPIO pins. These include an RC522 RFID chip, a magnetic door sensor, and an SG90 microservo. The servo drives a standard deadbolt core via a custom 3D printed mechanical adapter. Lastly, the Pi communicates to a server laptop, which stores the facial recognition information. The Pi uses Wi-Fi to access a SQL server, which stores RFID credentials and specific addresses for images used in facial recognition program. The Pi then uses the secure file transfer protocol to access the specific images using these addresses. Not included in the diagram is a standard LED connection to the GPIO pins, which was added in our final project presentation for visual feedback.
The system's continuous operation mode begins with waiting for the user to scan their RFID card. Upon scanning the card, the RFID number is queried from the SQL database, which returns a file path to the user's images in the file server. In the case that the RFID is invalid, the process begins again from the beginning wait state. If the RFID returns a match, the photos are then processed using OpenCV for facial recognition. In the case of a match, the unlocking process occurs, and in either case, all downloaded photos are removed prior to the next scan.
We chose OpenCV to run our facial detection/recognition for multiple reasons. The code is open source and well documented, which makes it easy to work with. OpenCV also allows us to choose our models so we're able to prioritize performance for our setup. We chose to use the LBP cascades because, although it is the least accurate on average, it is the most performant, which we needed in our Pi 4. The system scans through images of faces from the database, scans for faces through a live camera feed, then finally checks if the detected face matches the database faces.
In order to organize and transfer files between the main system and the file server, we chose to use a combination of a SQL server in conjunction with secure file transfer protocol. This allowed us to store user data away from the local device and create a layer of security between the site of user interaction and the photos necessary for the facial recognition algorithm to obtain. The SQL database allows the system to quickly query the needed data, and the SFTP allows for necessary photos to be quickly transferred between the file server and main system.
Our user interface is designed with simplicity and efficiency in mind. It guides users through the process of scanning their RFID tag, followed by facial verification. Each step is clearly outlined on the screen, with prompts and feedback to ensure a seamless interaction. This not only enhances user experience, but also upholds the strict security protocols of our system, making sure that each access attempt is both secure and straightforward.
The hardware included in the deadbolt system starts with a standard deadbolt core. The core is mechanically connected to an SG90 microservo via a custom 3D printed adapter. The servo is then directly connected to the Raspberry Pi 4's GPIO pins. Along with the deadbolt and servo, the system includes a magnetic door sensor mounted to the door that is also directly connected to the Pi's GPIO pins. The software for the deadbolt system is fairly straightforward. The SG90 servo uses the Raspberry Pi 4's pulse width modulation libraries to drive the servo to a specified position. The servo begins with a specified duty cycle that positions the servo to lock the deadbolt. Once the system grants access to the person scanning in, the Pi then changes the duty cycle of the PWM signal to rotate the servo approximately 90 degrees, which unlocks the deadbolt. The system then waits 10 seconds for the user to open the door before checking the magnetic door sensor to see if the door is still open. Once the door is closed, the magnetic door sensor pulls the GPIO pin circuit closed, indicating to the Pi that it is safe to lock the deadbolt again. The Pi then changes the PWM duty cycle back to the original value, which moves the servo back to the initial position, locking the deadbolt. The system then cleans up the GPIO pins for the next iteration.
We chose the Raspberry Pi 4 to be the base of our project. The Pi 4 has 4 GB of RAM, which is enough to run our OpenCV models. While the processor on the Pi 4 is relatively slow, it is still fast enough to run our code. The Pi 4 also has GPIO pins, which are necessary for interfacing with all of our hardware.
The system uses an RC522 chip in order to read and write the information to and from the RFID cards the user carries. The RC522 chip is connected directly to the Raspberry Pi 4's GPIO pins utilizing the standard SPI pin layout. The Raspberry Pi 4 then uses the MFRC522 libraries to read and write the information to the RFID cards using SPI functionality. The Raspberry Pi 4 operates off an uninterruptible power supply system that was designed for the Raspberry Pi 5. Unfortunately, we were forced to use the Pi 4 due to a pin address issue. Because of this, we had to modify the UPS in order to power the Pi 4. We did this by adding electrical tape to insulate certain connections, causing the Pi 4 to short out. The UPS uses 4 18650 battery cells that allow the Pi 4 to run up to around 12 to 16 hours uninterrupted in the event of a power outage.
The CAD design for the system housing went through several iterations in order to try and fit all the peripheral connections in as small of a package as possible. The walls are 2 millimeters thick, and the lid is a basic design that closes and holds with friction. The housing also contains a cut-through on the backside to route wiring for the deadbolt components as well as a port on the bottom for HDMI access. The design for the deadbolt assembly was rather simple and required no modification from a traditional deadbolt assembly. By following manufacturer instructions, no modifications to the door would be necessary, and the magnetic sensors mount on the inside surface of the door.
Our current system isn't without its challenges. The facial recognition process can be slow, which might be a bit frustrating for users in a hurry. Additionally, we don't have depth sensing, which would help us differentiate between a real person and a photograph, enhancing security against more sophisticated spoofing attempts. While there are other drawbacks to the system, these two are the main drawbacks that cannot be solved without major contribution of time and resources.
As previously mentioned, there are a couple of main obstacles for the system that should be addressed if this project were to continue. However, there are a few things that could also be addressed with much less time needing to be dedicated. One area for improvement is with the deadbolt system. Currently, there is no way to unlock the deadbolt from the inside, and there is no way to mechanically unlock the deadbolt in the incident of power loss or a dead servo. Both of these present some security concerns, but could also be easily remedied with more time. With regards to the main system with the Pi 4, an improved processor with compatibility with Intel's RealSense SDK would help remedy the issue of recognition time, as well as allowing for depth sensing capabilities using Intel's RealSense camera line. While there are other areas for improvement, these are the areas that would bring the greatest improvement to the system given the project's goals and deliverables. Overall, this project served as a great experience and taught us a lot about computer vision, Python, SQL, and more. This experience was unlike the semester before, as we had a lot more freedom as to how the project progressed. This helped us in some aspects, but also presented its own challenges as well. While we weren't able to meet all of our goals, like achieving depth sensing, we managed to accomplish most of them and create a complete, functioning product that demonstrates practicality and growth. Thank you for tuning in to our project overview.